Welcome. This video is going to take a look at using dimensional analysis with balanced chemical equations. If you remember back when we were working with balanced equations, they tell us how many of each atom or molecule are needed for the reaction to happen. So remember, your skeleton equation is like your shopping list of ingredients, but the balanced equation is telling you how many of each kind of substance you need, whether it's atoms or molecules. The problem is, in the lab, we can only measure chemicals by their mass or volume. Atoms are so ridiculously small, we can't measure out even 1,000,000 atoms easily. It's still, for most substances, 1,000,000 atoms is still too small an amount for us to see with our eye. So that means we need to be able to convert the mass of particles to the number of amount of particles, or vice versa. So this is kind of like if you had 1,000,000 pennies, you wouldn't want to have to count out all those pennies, put them into stacks of 100 to know how many dollars that is. You'd want to do it more quickly. And the way, coin sorting machines often do that is not only by the size of the coin, but then the weight of the coin. So in science, we use a unit called the mole, and the mole is often even referred to as a chemist's dozen. Just like a dozen or 12 of something helps organize and count things more quickly than counting them one at a time, a mole counts lots of particles at once. So it's a really big number to measure really tiny stuff like atoms or ions or molecules or electrons. And since there's several tiny things in chemistry that we like to measure, we just call these tiny things particles. So particle is just a generic name for either atoms, molecules, formula units if it's ionic, or even electrons and ions. It's also known as Avogadro's number because this is the fellow who came up with the idea of the mole, and as we'll see a little later, he came up with a really clever idea. So for now, what we need to know is that a mole is a chemical mass unit, so a unit, just like an inch or an hour, that's defined to be 6.02 times 10 to the 23rd molecules, atoms, or some other unit. So 6.02 times 10 to the 23rd is the number Avogadro came up with and said that many atoms or molecules or any other thing is 1 mole's worth. So the mole is a counting number. Just like a pair counts 2 at a time, a quartet counts 4 at a time, a dozen counts 12 at a time, a mole counts a whole bunch of particles at a time. It doesn't tell you anything about their mass or anything about their volume. It's a huge number, but it's still just a counting number, just like a pair or a dozen. So remember, a mole is 6.02 times 10 to the 23rd particles. I've written it as an equality here because that means we can set up 2 conversion factors, 1 mole per 6.02 times 10 to the 23rd particles, or 6.02 times 10 to the 23rd particles per mole. And if you want to see how big that looks written out, I've also typed it out there with all the zeros. So before we look at some examples, I just want to try and give you an idea of just how crazy big this number is. If you had a mole of marbles, just small little marbles, they would cover the entire Earth to a depth of 50 miles. Now 50 miles is like way deeper than even our atmosphere. The atmosphere only goes up about a mile. So that's a crazy amount of marbles. If you had a mole's worth of water glasses, so let's say 8-ounce glasses of water, 6.02 times 10 to the 23rd glasses of that water, it would fill all the Earth's oceans. If you had a mole's worth of paper, sheets of paper, just your regular printer paper, it could form not just 1 stack, but 1,000,000 stacks that would all reach past the sun from here on Earth. And if we had a mole's worth of pennies, you could divide all those pennies among all the people of the world, and everyone could spend $1,000,000 per hour, every hour, day and night for the rest of their lives. That's a crazy amount of things. But here's the really crazy part. A mole of water molecules is equal to only a little more than a teaspoon of water. How can that possibly be? Well, what this means is atoms and molecules are just ridiculously small, which means a mole has to be ridiculously big so that even a mole's worth of water is enough for us to measure. Just a teaspoonful, but enough to measure. So let's look at some examples of using it. Remember, our equality is 1 mole equals 6.02 times 10 to the 23rd particles, or whatever you're interested in. So my first example says how many moles are in 3.58 times 10 to the 23rd formula units. So just like we did before, I'm going to write down what I have, 3.58 times 10 to the 23rd formula units. So units is what I have, moles is what I want. So that means moles should go on top. The particles, or in this case formula units, should go on the bottom. So that means 1 mole divided by 6.02 times 10 to the 23rd. Now remember, in order for your calculator to know that that's all one number, you either have to type in all those zeros or you have to put parentheses around the bottom. And it's up to you which way you want to do it. Just make sure you do it. So if I take the 3.58 times 10 to the 23rd and divide by 6.02 times 10 to the 23rd, I come up with 0.595 moles. And I'm going to keep 3 decimal places because remember, sig figs, especially when you're multiplying and dividing, if you start with 3 digits, then you should end with 3 digits. My second example, how many atoms are in 0.88 moles? Again, I write down what I have, 0.88 moles, and what I want atoms, which is a type of particle. So now I need to set up with my atoms on top, moles on the bottom. So now Avogadro's number goes on top, 6.02 times 10 to the 23rd atoms over 1 mole. And if you want to put this in parentheses, you can, because we're multiplying all 3 terms here. It doesn't matter. I'll let you decide if you want to be consistent and always use parentheses. But 0.88 times the 6.02 times 10 to the 23rd is going to give me 5.3. I'm just going to keep 2 sig figs since I only had 2 here. 5.3 times 10 to the 22nd atoms. So here's 2 examples for you to try on your own. Not a lot different than what we just did. So I'd encourage you to pause here and see if you can do these and come up with the same answers as I do. I'm starting with 1.35 moles. I'm trying to get to molecules. Now moles is abbreviated MOL. Molecules doesn't have a shorter abbreviation, which seems kind of crazy, but we don't use molecules in equations very often. The reality is we're actually usually going to be converting between moles and grams rather than the actual number of particles. Particles are just too small. We need a mole's worth to do anything, or close to a mole's worth, so that's kind of how we deal with them. So at any rate, I want molecules, so I'll write it out since there's no abbreviation. I have moles, so my unit would be 6.02 times 10 to the 23rd molecules in 1 mole. So then when I take my 1.35 times 6.02, I'm going to come up with 8.127, or I can abbreviate that to just, or I should say round it to 8.13 times 10 to the 23rd. And because it's molecules again, I'll go ahead and write out the whole unit. My second problem, if I have 2.54 times 10 to the 15 atoms, how many moles is that? Well, since I want moles, I need to put moles on top, have atoms, put that on the bottom, and I know there's 6.02 times 10 to the 23rd atoms, molecules, whatever, in 1 mole. And you should notice that 2.54 times 10 to the 15th is less than 1 mole. So when I take this and divide by the 6.02, it's not a big surprise that I'm going to get less than 1 mole's worth here. So I get a final answer of 4.22 times 10 to the 9th moles.